Right now, I mean, literally at this exact second, your phone is juggling millions of invisible
Oh,
packages.
easily millions.
Yeah, and it is sorting them into like 65,000 different invisible doorways, sending them all across the globe. And it's doing all of this in milliseconds.
It's kind of wild when you actually stop to think about it.
It really is. It's so incredibly easy to take that for granted, you know? We open a laptop, we tap a link, and it just works. It feels a little bit like magic.
Right, but there is zero magic involved.
Exactly. The reality is behind every single tap on your screen, there's this massive, highly organized logistics network just churning away. So welcome to today's deep dive.
Glad to be here for this one.
Our mission today is to completely demystify that invisible network for you. We are going to take the quote-unquote magic of the internet and break it down into a series of logical, fascinating mechanisms.
And to do that, we are diving into some really fantastic foundational material today.
Yeah, we've got some great sources.
We do. We're drawing from IT Certification Training Materials by Professor Messer. Specifically, we're focusing on the foundations of IPOA, the Internet Protocol, and the
Right.
common ports that dictate exactly how our devices talk to each other.
And I want to be clear right out of the gate here. Even if you are not actively studying for an IT exam, this deep dive is entirely for you.
Oh, absolutely.
This is basically the ultimate shortcut to understanding what actually happens under the hood of your digital life. It is for anyone who wants to know how this whole digital world actually holds together.
It really is the ultimate behind-the-scenes tour. And, to set the stage, it helps to think about the physical connections first.
Like the cables or stuff.
Right. We hear a lot about Ethernet cables, wireless routers, fiber optics. But from the perspective of the protocols we are unpacking today, those physical networks are just, well, they're just the roads.
Just the asphalt.
Exactly. Just the asphalt. What really matters is the traffic driving on those roads.
So before we can understand where all our data is going, we kind of have to understand how it gets packaged and shipped in the first place.
Right.
And the source material uses this brilliant analogy of a moving truck. If the network, like the Wi-Fi, is the physical road, then the Internet Protocol, or IP, is the moving truck driving on that road.
I love that analogy because just like a real moving truck, you don't just throw loose items into the back and, hope they survive the trip.
Right, that would be a disaster.
It would be a complete mess. You pack things carefully into boxes first.
So inside this IP moving truck, you have boxes. And in the networking world, those boxes are either TCP or UDP protocols.
Oh,
And then finally, inside those boxes is the actual data you care about, like the web page you're trying to load.
yes.
It is essentially a digital set of Russian nesting dolls. And the source material actually has a formal name for this nesting process. They call it encapsulation and decapsulation.
That's the technical term, yeah.
Yeah. You encapsulate the data in a box, put the box in a truck, send it, and the person on the other end decapsulates it to get the item out.
And those two types of boxes you mentioned, TCP and UDP, they are really the foundation of everything we do online.
Let's break those down. Let's look at TCP first.
Sure. So TCP stands for Transmission Control Protocol. And TCP is what we call connection-oriented.
Meaning it has like a strict set of manners.
That is a great way to put it, actually. There is a highly formal process for starting and ending a conversation.
How so?
Well, the material compares it to a phone call. Think about it. You dial the number. The other person picks up and says hello. You say hello back. You have your conversation.
Right.
Then, crucially, you both mutually agree to say goodbye before you hang up.
There's an undeniable structure to it. You don't just walk away from the phone.
Exactly. And because of that structure, TCP provides what we call reliable delivery. It uses a system of acknowledgments.
Like delivery receipts.
Yes, exactly like that. When the TCP box is delivered, the receiver essentially signs for it and sends a receipt back to the sender.
Oh, that makes sense.
And if a box gets lost or damaged on the road, the receiver lets the sender know, and the sender ships a replacement. TCP also features flow control.
Flow control. Like, what does that mean in this context?
I mean, if the receiving computer is getting overwhelmed with, too many boxes arriving at once, it can literally tell the sender to slow down. It just says, hey, I lack the capacity to process everything. Give me a second.
Okay, let's unpack this, because this makes perfect sense for TCP. It's careful, it checks its work, it makes sure everything arrives intact.
It's very thorough.
Right. But then we have the other box, UDP, the User Datagram Protocol. And the source material says UDP is connectionless.
Very connectionless.
It provides unreliable delivery. There's no flow control and there are no acknowledgments. So my question is, why on earth would anyone want a delivery service that just throws packages out the back of a speeding moving truck without even checking if they landed on your porch?
It sounds crazy, right? But what's fascinating here is that sometimes speed is vastly more important than perfection.
Really? More important than actually getting the data.
Yes, you pointed out how careful TCP is, but that carefulness creates a lot of overhead.
Because of all the receipts.
Right, all those acknowledgments, the flow control, the formal hellos and goodbyes, that takes processing time. GDP strips all of that away. It has virtually no overhead.
So it's just pure speed.
Exactly. It just sends the data as fast as humanly possible,
It literally just throws it out the truck window as it drives by.
basically. And the source gives a great example of when you want exactly that. Real-time communication. Think about voice over IP phone calls or live video streaming.
Oh, like a Zoom call.
Right. If you were on a live video call and a packet of data gets lost in transit, it doesn't do you any good for the computer to ask for a replacement packet 2 seconds later.
Right, because time has already moved on. You can't really rewind a live conversation.
Exactly. If a UDP packet drops, maybe the video glitches for a millisecond, or maybe a single word drops out of the audio. But what do you do as a human?
You just say, sorry, could you repeat that?
Yes. The application doesn't try to fix it automatically behind the scenes because in real time, late data is useless data.
That makes total sense.
Yeah, UDP is absolutely perfect for scenarios where you need raw speed and you are perfectly willing to accept a few drop boxes along the way.
Okay, so we have our IP moving truck driving down the road. It's loaded up with either careful TCP boxes or fast UDP boxes. But how does the truck know exactly where to park?
That's the next big piece of the puzzle.
And when the movers carry the boxes into the building, how do they know which room gets which box?
Right, so this is where we move from the truck to the destination. To find the right building, the truck uses an IP address. You've probably seen these.
Yeah, something like 10.2, right?
Exactly. It acts exactly like a street address for a device on the network.
Mm.
But getting to the building, however, is only half the battle.
Because a single server out there on the internet is a really busy build-out. I mean, it might be running a web server to host a site, an email server to handle messages, and a voice server to handle calls, all at the exact same time.
Oh, absolutely. They handle massive workloads.
So if the moving truck just dumps all the boxes in the lobby, the server has no idea what data belongs to the website and what belongs to an email, right?
That is exactly why we have port numbers. Every service running on a machine is assigned a specific port number between 0 and 55,535.
That's a lot of ports.
It is. And this creates what we call multiplexing.
Yeah, the source material uses that term, multiplexing. It sounds like a movie theater, but I couldn't quite connect the dots on how that applies to a server.
Well, think of a literal multiplex cinema. The building itself has one single street address, say 123 Main Street.
Okay, so that's the IP address.
Right. But inside that building, there are 20 different screens showing different movies simultaneously. If you just show up at the front door of the building, the ticket taker doesn't know where to send you.
Right, you need a ticket that says Theater 4.
Exactly. Ports are those theater numbers. They allow the server to take in multiple different streams of traffic at the same time and perfectly route them to the correct internal application.
Okay, here's where it gets really interesting. As I was reading the source material, I realized it's not just the big servers out on the internet that use these port numbers.
No, not at all.
Your laptop, sitting right in front of you, is using them too. The material makes a really clear distinction between non-ephemeral ports and ephemeral ports.
And that's a vital distinction. So the servers use non-ephemeral ports. These are well-known permanent ports, generally numbered from 0 up to 1023.
Okay, so why are they permanent?
Because if you want to visit a web server,
Yeah.
you need to know exactly what door to knock on every single time. It can't just be changing randomly or you'd never find it.
But when your laptop reaches out to that server, it uses an ephemeral port. An ephemeral just means temporary. So your computer picks a random high number, somewhere between 1,024 and 65,535, and uses that as its return address for that specific conversation.
Exactly.
And the second you close the web page, that temporary port is just tossed back into the pool.
Yep. So when the server replies with the website data, it addresses it to that temporary ephemeral port on your laptop.
Which is how your laptop knows, this data goes to that specific Chrome tab the user just opened.
You've got it. It keeps everything perfectly organized on both ends. But we should probably clarify something else, though. TCP port 80 is an entirely different destination from UDP port 80.
Oh, right. Even though they have the exact same number, they are expecting completely different types of boxes.
Yes, they share the same numbering scheme from 0 to 65,535 at war, but a TCP port and a UDP port with the exact same number are completely separate entities.
It's like Theater 4 on the first floor versus Theater 4 on the second floor.
That's a perfect way to look at it. And this raises an important question that the source material points out. Because we talk about these ports like doors to a building, it's very easy to assume they are a security feature.
Yeah, I mean, they do sound like locks on a door.
They really aren't. Port numbers are absolutely not security mechanisms. They're purely reference numbers.
So anyone can just change them.
Yes, anyone can change the port a service runs on. Now, firewalls do use these port numbers as criteria to decide whether to block or allow traffic to pass through. But the port number itself is just a routing instruction.
Well, since firewalls govern our networks based entirely on these reference numbers, let's open the doors and look at some of the VIP rooms of the internet.
Let's do it.
Let's explore the specific well-known ports that every IT professional has to memorize. And I want to start with one I read about that is practically being boarded up forever.
I think I know which one you mean.
Let's talk about command line administration tools, specifically Telnet, on TCP port 23.
Right. So Telnet is an older protocol that gives an administrator a remote command line to control a device.
Okay.
Visually, it looks like you are sitting right in front of the server typing in commands, but it has a massive, massive flaw by today's standards.
Let me guess.
It has zero encryption.
Yeah, the source material stresses that everything sent over Telnet is sent in the clear.
Every single thing.
Which means if you log into a router using Telnet, your username, your password, every single command you type,
Yep.
It is all just flying across the network in plain text.
Yep. Anyone listening in on the road can read the contents of that moving truck without even trying.
That is terrifying.
Which is why almost every organization today outright bans the use of Telnet. It's just way too dangerous. The modern standard is its replacement. SSH, which stands for Secure Shell.
And what port does that use?
SSH operates on TCP port 22. Functionally, it does the exact same thing as Telnet. It gives you a remote command line. But SSH provides a fully encrypted communication link.
So if someone is snooping,
anyone listening in on the network just sees scrambled, completely useless data.
So port 23 is the insecure past, and port 22 is the secure present.
Exactly. And if we connect this to the bigger picture, this exact evolution from clear text vulnerability to mandatory encryption, it happened with everyday web browsing too.
Oh, this is something everyone listening uses every single day.
Absolutely.
For the longest time, we used HTTP, the Hypertext Transfer Protocol, to browse the web, right? Operating on TCP port 80.
That's the standard.
But just like Telnet, standard HTTP is entirely unencrypted. So if you type a credit card number into a standard HTTP site on port 80, it went across the entire internet in plain text.
And obviously that became a massive liability as the internet grew into a commercial space. You can't have credit cards flying around in the clear.
So we evolved to HTTPS, the secure version of the protocol, which runs on TCP port 443.
Right.
And today, almost every page you visit, every bank you log into, every video you stream, it is traveling securely encrypted over TCP port 443. Port 80 is basically just kept around to redirect people to the secure port now.
It is a phenomenal example of how these protocols adapt to our changing security needs. But let's step back for a second, though.
Okay.
We just talked about browsing the web. But when you want to visit Professor Messer's website, you don't type 162.159.246.164 into your browser.
No way. Humans are terrible at remembering numbers like that. We type words. We type, www.professormesser.com.
Exactly.
But we just established that the IP moving trucks absolutely require an IP address to know where to go. So how does the network bridge that gap between the human words we type and the numbers the machines actually need?
It relies on a master translator, DNS. The domain name system.
Yeah.
And DNS operates on UDP port 53.
UDP, so it's fast.
Very fast. Every time you type a website name, your computer shoots a lightning-fast request out to a DNS server. It essentially asks, hey, what is the IP address for this name?
And then it just sends it back.
Yep. The DNS server checks its directory and fires back the IP address, allowing your computer to start sending the real web traffic.
And notice it uses UDP, folks. Because it's UDP, it doesn't bother with a formal handshake. It just shouts the question and gets the answer instantly.
Right, you don't even notice the translation happening. It's so quick.
That's awesome.
And because it is so vital, without DNS, the internet is practically unusable for a normal person. Networks almost always use multiple redundant DNS servers. If one goes down, there is always a backup ready to answer the call.
Okay, so that translation handles where we were going, but it actually brings up a really logical follow-up question.
What's that?
Well, I was thinking about my phone. I never, ever manually type an IP address into my phone when I connect to a coffee shop's Wi-Fi.
No, nobody does.
It just connects. So how does the device get its own street address to begin with?
It feels seamless, but it's a protocol called DHCP working behind the scenes. DHCP stands for Dynamic Host Configuration Protocol, and it operates using UDP ports 67 and 68.
Ah, another fast UDP-based system.
Exactly. When you connect to a network, your device essentially shouts out, "Hello, I'm new here, I need an IP address."
Just throws it out there.
Yep. And the DHCP server on the network hears that, look at its pool of available addresses, and automatically leases an IP address to your device. It also hands out other necessary info, like where that DNS server we just talked about is located.
The word lease is key there, right? You don't own it forever.
It is a temporary lease, much like renting an apartment. When the lease time is up, your computer will automatically try to renew it.
And if you leave?
If you disconnect and leave the coffee shop, that IP address eventually goes back into the available pool for the next customer to use. It makes joining a network completely hands-off.
That's so smart. But the source material notes that IT admins can tweak this. The material mentioned DHCP reservations. Why would an administrator want to intervene in an automated process like that?
Well, think about a network printer. If a printer's IP address changed every week when its lease expired, every computer in the office would suddenly lose connection to it and no one would be able to print.
Oh, that would be a nightmare.
It really would. So an administrator creates a DHCP reservation by telling the server, whenever this specific printer asks for an IP, always give it this exact same one.
Oh, so it combines the automation of DHCP with the stability of a static address.
Exactly. It's the best of both worlds.
So let's transition to a standard day at the office. We've got the roads built, the trucks moving, the addresses assigned, and the names translated. What protocols are carrying the actual work we do?
There's a few key ones.
Let's start with email, because we hit send and forget about it, but it actually takes a whole team of protocols to manage our inboxes.
It really does. When you hit send on an email, it doesn't go straight to your friend's laptop. It goes to a server. And sending that mail uses SMTP, the Simple Mail Transfer Protocol, on TCP port 25.
Okay, so SMTP handles the outbound journey, but pulling emails down from the server to your device requires a totally different doorway.
Right. Traditionally, we used a protocol called POP3 on TCP port 110 to retrieve mail.
I remember setting that up back in the day.
Yeah, but POP3 is fairly basic. It simply downloads the mail and usually deletes it from the server. Today, most of us use IMP4 on TCP port 143.
And the material points out that IMP4 is vastly superior for how we work today.
Undoubtedly.
Because it allows you to manage folders, and it actually syncs those actions across all your devices. Like if you read an email on your phone, it talks back to the server, and the server updates it so it shows as read on your laptop.
Exactly.
That multi-device synchronization is IMP doing all the heavy lifting on port 143.
It's a protocol designed for a modern multi-device workflow.
Totally. Now, there's another office scenario that always fascinated me, dealing with massive files.
Yeah.
If I'm sending like a 50 gigabyte video file to a client, standard email obviously won't cut it. The source material talks about FTP, the file transfer protocol. But I was really surprised to see it uses 2 ports.
Yeah, FTP is quite unique in that way. It uses TCP port 20 for the actual active data transfer, and TCP port 21 is the administrative control port to send commands.
But why separate them? Why not just do it all through one doorway?
Well, imagine trying to tell a server to pause or cancel a download, right? But your tiny little pause command gets stuck in a massive traffic jam behind the 50 gigabyte video file itself.
Oh, it would just time out.
Exactly.
Yeah.
By having a dedicated control lane on port 21, your administration commands completely bypass the heavy data traffic on port 20. It basically acts like an HOV lane for instructions, so you always maintain control of the transfer.
That is brilliant. Okay, so FTP handles sending files out across the internet, but what about just moving a spreadsheet to the desk next to you or sending a document to the office printer? Do Windows machines use FTP for that internal office chatter?
No, actually. In a Windows environment, local file and print sharing is dominated by SMB, the Server Message Block Protocol.
Okay, SMB.
Now, older Windows devices relied on a protocol called NetBIOS to handle this, which operated on UDP 137 and TCP 139.
But NetBIOS is mostly a relic of the past at this point, right?
Mostly, yeah. Modern Windows systems use direct communication for SMB, bypassing the need for NetBIOS entirely. And that modern direct communication happens over TCP port 445.
Got it.
That is the invisible doorway your computer uses when it suddenly detects, the new scanner down the hall.
Nice. Now, what about this? You know when you call the IT help desk and they ask to take over your mouse to fix something?
Yes.
It's slightly terrifying, but also incredibly useful. How are they physically painting your desktop screen onto their monitor miles away?
They are using RDP, the Remote Desktop Protocol. This allows an administrator to view and interact with the desktop of a remote device. And it operates on TCP port 3389.
And that's just for Windows.
While it's a Windows protocol natively, you can actually get RDP clients for Mac, Linux, and even your smartphone nowadays.
Okay, one more. And finally, before any of these file transfers or remote desktop sessions can happen, the network has to actually verify who you are.
All right, security is key.
When you log into your work computer, how does it know your password is correct and what folders you are allowed to see?
For that, we use LDAP, the Lightweight Directory Access Protocol, on TCP port 389.
LDAP.
Yes. It is the protocol used to search and access centralized network directories like Microsoft's Active Directory. Think of it as the bouncer checking the guest list. It lets the network verify your credentials against the master database.
So what does this all mean? We started out talking about the magic of the internet, but it's not magic.
Not at all.
Behind every single click, every video call, every sent email, there is an incredibly organized fleet of IP trucks.
Yep.
They are carrying connection-oriented TCP boxes or super-fast connectionless UDP boxes. They are navigating via IP addresses, dropping temporary ephemeral ports, and perfectly docking at highly specific numbered doorways like 443 for the web or 53 for DNS to deliver their cargo. It is a stunning logistical achievement.
It really is. And when you understand these ports, you basically understand the foundational language of the entire network.
I completely agree. But I want to leave everyone with a final thought, building directly on a nuance we discussed earlier.
Oh, sure.
We established that port numbers aren't actually security features, right? They are just reference tags.
Right, just labels on a door.
We also established that standard firewalls are usually programmed to block the bad port numbers and leave the good web ports, like our secure HTTPS port 443, wide open.
Because otherwise, nobody inside the building could browse the web.
Exactly. But if port numbers are just tags and port 443 is universally left wide open for web traffic, what stops a malicious actor from simply disguising their dangerous, unauthorized traffic, tagging it with port 443, and driving that moving truck right through the firewall's front door?
That is a very, very good point, and it completely highlights why network security is such a complex, ever-evolving challenge today.
It makes you look at that invisible fleet of trucks a little differently, doesn't it? It's all about what's actually inside the truck. Thanks for joining us on this deep dive. We'll catch you on the next one.